So now that we have looked at the definition of the upper Riemann sum of our function over some dissection D, let's have a look at the definition for the lower Riemann sum. So firstly, the notation, we'll use capital L for lower Riemann sum, and then we'll subscript it D to say that it's over the dissection D, and then it's of the function f. So the definition of this is, again, we're thinking about our dissection D being set, and let's say it partitions the interval AB up into little n pieces. Then it is the sum from I is equal to 1 to n of, again, the length of those intervals, xi minus 1, and this time from each of the intervals we're going to multiply the horizontal length by a vertical height, but this time we're going to pick the smallest possible value within each interval. Now, more generally, so that our definition can operate on a broader range of functions, we're not going to assume that it obtains its minimum over each one of these dissected intervals. Instead, we'll put in the infimum there, which is guaranteed to exist because I've said my function f is going to be bounded on the entire interval AB, so it's going to be bounded below everywhere on the interval AB. And therefore, for all of these cut-up intervals, it's going to be bounded below. So the infimum over x is allowed to vary on the interval xi minus 1 to xi, and then it's of the values of f of x. So that's the definition for the lower Riemann sum. Just to make sure this is absolutely crystal clear, let's draw a picture to show what this represents. So again, we'll have our interval AB here, and we'll draw the positive function case because that's the one we all prefer to think about. So for the sake of simplicity, we'll just dissect this interval up again into 3 pieces. So at start, it's going to be the sum from I is equal to 1 to 3 of the length of these intervals xi minus 1 times the infimum from each of the intervals xi minus 1 to xi of the values of f of x. So writing this out, so it's going to have 3 parts to it. The first interval is going to be a to x1, and we're going to need that length, so it's this horizontal length here, so x1 minus a times the infimum. Now again, because on the picture I've drawn a nice continuous function, by the extreme value theorem we know that continuous functions obtain their minimum and maximum on a closed interval, so it's actually going to have a minimum over that interval, which will be the infimum. But as I say, to keep it more general, we put infimum so that it can operate on functions that aren't as beautiful as the one that I'm actually drawing in the picture here. So you can see that the minimum value is really here. So we're multiplying the horizontal distance by that vertical height. So therefore we're overall going to end up with that area shown there by that rectangle. So this is the infimum over x is allowed to be between a and x1 here, where this is x1, and we'll call that x2, of the values of f of x. So some colour now. In red there, that rectangle's area corresponds to this bit of the Riemann sum, the lower Riemann sum. Now, next bit, we're going to move on to the next part of the dissected interval, so it's going to be plus x2 minus x1, that horizontal length there, and then again, the infimum is going to be the minimum in this case, and you can see it's around there on this picture, so we're going to get a rectangle that looks something like that. So times that infimum for x is an element of x1 to x2 of f of x, and that corresponds to that area, so we'll colour that in green there. And then the final one as well, so you'll have plus, and it will be b minus x2 times the infimum of x is an element of x2 to b of the values of f of x, and the sort of smallest value for this interval is around there, so that'll be the area of this rectangle here. And we'll colour that in yellow. So that's this concept of the lower Riemann sum illustrated for this very simple dissection of the closed interval AB into three parts. However, this same corresponding picture goes on for all the much more complicated dissections. You could be dissecting this closed interval up into potentially 1 million pieces, and this same understanding of what the lower Riemann sum over that dissection for our function is holds true. So you can intuitively see that if you have the lower Riemann sum over any dissection of our function over this interval AB, it's always going to give a value less than or equal to the intuitive concept of the area under the curve. So overall, what we intuitively understand is that this thing that we're after, the integral being this area underneath the curve, it's going to be bounded below by all the lower Riemann sums for every single dissection. Any dissection you put here, this is going to be true. So all of these are going to be less than or equal to this. And then it's going to be bounded above by all of the, and I'm sorry, I'm going to a different notation. So in some notations, we use capital S to mean a upper Riemann sum and lowercase s to mean a lower Riemann sum. And I was just about to flit back into that notation, but I've corrected myself. So here are all the upper Riemann sums that are always going to be greater than or equal to the value of this intuitive thing that we're after being the value of the integral. And of course, equality will hold here when the function is very simple. When it's a constant function, then all the lower Riemann sums and the upper Riemann sums will all give the same value, and they'll give the value of that area under the curve. Now, as we did for upper Riemann sums, let's just say a little bit about how this works for functions when they're negative rather than positive. So just drawing a picture here. So remember, for upper Riemann sums, when they're positive, the value that you're getting is the largest modulus value, and when they're negative, the value you're getting was the lowest modulus value, because it's always the most positive, the least small. But as far as modulus is concerned, that flipped when you went from one side of the x-axis to the other. For lower Riemann sums, when you're above the x-axis, you're picking the smallest modulus value, but when you're below the x-axis, you're then going to be picking the biggest modulus value. So if we have a function like this over our interval AB, and again, let's just dissect it. In fact, we might even do even simpler dissection. Let's just dissect it into two parts. So the lower Riemann sum here, so for this interval, we'd want the minimum bit, so the most negative. So I think probably this bit wins over this bit just about. So we'd be making a rectangle like this. And for this next bit, this is probably the most negative bit, so we'd be making a rectangle like that. So that would be what the lower Riemann sum would come out as. And it's actually going to be a larger modulus number overall than the upper Riemann sum, but of course it's going to be more negative, so it's going to be less than the upper Riemann sum. So now that we know what the upper Riemann sum and the lower Riemann sum are, we're going to head towards the definition of the Riemann integral, but before we get there, it'll pay for us to do a little bit more work on upper and lower Riemann sums first. So the first thing I want to tell you about is what is meant by a refinement of a dissection. So we're now going to consider two dissections, D1 and D2, and I want to tell you what it means for D2 to be a refinement, a refined version of D1, a refinement of D1. So if we have our interval here, AB, and let's say here is our dissection D1, so it's this sequence of cuts. So D1 would be this sequence A, and then x1, x2, and in the case of this picture, we've only got 4 cuts, so x1 all the way up to x4, and then we'd have the endpoint B. So that would be D1. For D2 to be a refined version of D1, or a refinement of D1, it means that it's a bigger dissection, so you've got more cuts, but it still keeps all of the original cuts from the original dissection. So all of these are going to be kept, you're just going to add in more cuts. So that's probably what you would have guessed as being the meaning of refining a dissection. So I'll do this in another colour. So we'll add in some more cuts. We'll cut here, we'll cut here, we'll cut here. So let's call these new points. We'll call that y1, that y2, that y3. So the new dissection, D2, that refines D1, is going to be A, then Y1, then X1, then Y2. So just labelling up the points here. This is X1, this is X2, this is X3, this is X4. So you have to keep all the old cuts from the original dissection if it's a refinement. So putting them in order in this sequence, we've got A, Y1, X1, Y2, and then we'll have X2, X3, Y3 comes next, X4, B. So that's the new dissection, and this one now is a refinement of that one. So it has to contain the original points. If I took out one of these cuts, say I got rid of X2, decided I didn't want to cut there anymore, got this out, this new dissection that I had there, we could call it D3, would not be a dissection of D1 because it doesn't have all the old cuts from D1. So a refinement has to have all the cuts from the original one and then it's got a few more. So that's what is meant by a refined dissection. Now, if you take a dissection and refine it, then the upper and lower Riemann sums are going to become better approximations to the area. The upper Riemann sum is going to get smaller, i.e. going towards the area, because they're always bigger than the area, so if it gets smaller it's coming in towards it. And the lower Riemann sum is going to go up, i.e. towards the area. So let me just formally show you that. So we're going to say that D2 is a refinement of D1, and we want to show that, let's start with the lower Riemann sum, that the lower Riemann sum of D1 over D1 of F is less than or equal to the lower Riemann sum over D2 of F. And then we'll also show for the upper Riemann sum that the upper Riemann sum of F over D2 is less than or equal to the upper Riemann sum over D1 of F. And remember, somewhere in between here is the actual area that we want. Remember, all the lower Riemann sums are less than or equal to this, all the upper Riemann sums are greater than or equal to this. So by refining the dissection, we are getting closer to it, because this one's coming down and this one's going up. So both of the lower and upper Riemann sums get closer to the actual thing that we're after when you make a refinement to your dissection. So let's start by looking at this one. So this follows really simply just by actually looking at the definition. So we'll write down the definition again for the lower Riemann sum over a dissection of the function. It's equal to the sum from I is equal to 1 to n of xi minus 1 times the infimum of x is an element of xi minus 1 to xi of the value of f of x. Now, if we go to our picture up here, for the original dissection, D1, we were using these lengths here, and we were multiplying them by their infimum over there. If we just consider one of these for the time being, so to simplify it, let's just firstly consider this bit, this part of the original Riemann sum of D1. So for D1, part of that Riemann sum was this x1 minus a, that's the length of the interval, times the infimum of the values of f over the interval from a to x1. And I might drop the f of x just to make it slightly shorter, just put f there. Now, when we did the refinement, for each of the intervals in the original dissection, you've either left them the same, so this one got left alone, it didn't get cut up further, or you've cut them up further, but this one, it's been cut in half, it's got a new point there, cutting it up. So, what we could do is we could write x1 minus a, the length of that original interval, as x1 minus y1 plus y1 minus a. So what have I done there? Well, we've added in that new point, which is y1, that's a new cut. So, of course, the length of this whole interval is just the length of this bit times the length of this bit. So I can write its length here as the length of this bit here, which is x1 minus y1, plus the length of this bit here. And now, if I substitute that in here, oops, sorry, I didn't mean to shake everything like that. If I substitute that in here and apply distributivity, then I'll get that this is equal to x1 minus y1 times the infimum of f over that interval, a to x1, plus y1 minus a times the infimum of f over x as an element of the interval a to x1. Now, this looks like what you would need as part of the first two terms of the lower Riemann sum over the dissection d2. So if we were doing the lower Riemann sum over the dissection d2, we'd need the length of this interval times its infimum over that interval, plus the length of this interval times the infimum over that interval. And look, we've got those two lengths of those intervals times an infimum, but these aren't the correct infima. These are the infima over the entire original interval that's now been cut in half, a to x1. But if you now compare, so if you consider comparing the infimum of the function f over the interval a to y1 and the infimum of f over the interval y1 to x1, these things are related to this. We can write an inequality here. They are guaranteed to be greater than or equal to those infima. So this one is greater than or equal to the infimum of f over that larger interval. And this one is also guaranteed to be greater than or equal to the infimum of f over that larger interval. And the reason is, you're looking at a set of values of f here and taking the infimum. The set of values of f for this is entirely contained in the set of values of f that you're taking the infimum of here. Here, you're going over that entire interval, a to x1. So if I just draw this out again, here is a, here is x1, here is y. So if you like, you're taking the infimum of the set of all the values of f over that entire interval here. Here, you're just taking the infimum of all the values of f over this smaller part. So all the values that are in this set that you're taking the infimum of will also be in this set, but this set's bigger. It's got all the values from here. So it's potentially got values that could be smaller than the smallest values in here. And I say smallest in sort of like quotation marks because, of course, it might be the case that it doesn't actually have a smaller value. But if you have a set that has more elements in, the infimum of that set with more elements in is always going to be less than or equal to the infimum of the original set. So this is basic set theory. If we have just two sets, x and y, and x is entirely contained in y, which is the case for this set. So this is our set x, and this is our set y. This one's entirely contained in this one. Then it is true that the infimum of the set x is always guaranteed to be greater than or equal to the infimum of the set y. Because if you imagine this is our set x, let's just show it with some red points here. So its infimum might be there. If you now go to this bigger set, it's got all those red points still in, but then it's got some more points. Now, if all the points are up here, let's say, in blue here, then it won't change the infimum, in which case the infima will equal one another. But if it's got some points down here, which it could have, then it will push the infimum down further. So when you've got containment in this way, the infimum of the one that is contained within the other one is always going to be greater than or equal to the infimum of the larger one. So that's what we're doing here. That's how we know this. This set is contained inside this set, so its infimum is going to be less than or equal to this one. And again, with this one, this set is contained inside this set. So the infimum over all values of f for this larger set is guaranteed to be less than or equal to the infimum of all the values of f over this set. So then what we can do is say that the thing, and I apologise, the wind is blowing quite heavily, the thing that we actually need in the lower Riemann sum over our refined dissection is guaranteed to be less than or equal to this thing. So we can say the other way around, greater than or equal to. So this is guaranteed to be greater than or equal to. So the thing that we actually want in our lower Riemann sum over D2 is going to be x1 minus y1 times the infimum of the values of f over that interval from y1 to x1. And we know that because this thing is greater than this thing, then when you multiply the two of them greater than or equal to this thing, then when you multiply them both by this constant, the inequality will still hold true. And similarly, we need y1 minus a times the infimum of all values of f over the interval from a to y1. And again, we know this thing is greater than or equal to this thing, so when you multiply by this constant, this is still greater than or equal to this, and then you've got this is greater than or equal to this is greater than or equal to this. So if you add these two things together, it's guaranteed to be greater than or equal to these two things. Now, this is of course equal to this because we got it by just substituting in this in place of this. So we've now got that this thing is greater than or equal to this thing. So what we have shown is that the corresponding terms in the refined dissections Riemann sum are greater than or equal to the term in the original dissections Riemann sum. So now that same argument is going to hold true for all of the intervals in the original dissection. So you can now go on to this next interval from x1 to x2, and the bit that will appear in its lower Riemann sum is going to be less than or equal to the corresponding bits, the two bits that you're going to then have in the new dissections lower Riemann sum. For this one, it's going to be exactly the same. For this one, again, it's going to hold true because you've split it further. So the original interval's contribution to the lower Riemann sum for the original dissection is going to be less than or equal to the two terms that you need in the new dissections lower Riemann sum. This one hasn't been cut any further, so they'll be exactly the same. So when you add them all together, you can see that the new dissections lower Riemann sum is going to be guaranteed to be greater than or equal to the original dissections lower Riemann sum. So we have shown this thing here.